All right, folks, our next section, section 3.8, the book titles it Implicit Differentiation, and I give it the subtitle that it is nothing more than more chain rule. So we learned in section 3.7 the chain rule, and at that time I stressed how important it was to master the chain rule and to get a good grasp of it. Well, the topic of this section, implicit differentiation, I'm telling you, it's going to be nothing more than the chain rule. So if the chain rule isn't really understood, this section, it's going to be a little bit more challenging than it should be. Now, before we get started, it is worth our time to discuss one more time that the derivative is a rate of change. In fact, you can think when you see dy dx, you could think dy dx, that's telling you the rate of change of y with respect to x. Likewise, dy dt, that's telling you the rate of change of y with respect to t. Or even a dv dt, that's telling you the rate of change of v with respect to t. So let's consider the following example. It's going to be one of the rare times that I don't head off to the chalkboard to work through an example. So let's consider the equation xy minus y equals 3. We are going to determine dy dx. We can do that right now, and here's how we would do it. We have to start by doing a little bit of algebra. I mean, you look at that equation, xy minus y equals 3, and on the left-hand side, we can factor out a y. And then after we factor out a y, we can divide both sides of the equation by x minus 1, and that gives us y equals 3 over x minus 1. Now, it's easy. It's going to be easy for us to get the derivative, dy dx. We have y equals 3 over x minus 1. But here's a little vocabulary. We say that y equals 3 over x minus 1. It is a function that was defined. It was defined implicitly by the equation xy minus y equals 3. So it's almost like disguised. The function of x was disguised in the equation xy minus y equals 3. And like I said, we can easily get the derivative from the y equals 3 over x minus 1. We can quickly get the derivative is negative 3 over x minus 1 quantity squared. So let's do a quick recap of that example we just looked at. Okay, we're going to look at what was implicit and then what was called explicit and what the derivative was. So the equation xy minus y equals 3, that's said to be implicit. That we see that there's a y in there and it's kind of disguised. It's a function of x, but we don't know what it is. But in the explicit form, we can explicitly see what the function of x is. It's 3 over x minus 1. Now, it doesn't matter the implicit form or the explicit form. The derivative was dy dx equals negative 3 over x minus 1 quantity squared. Now, this doesn't seem too bad. That process that, we just ran through in the first example, I mean, folks, it works well when we can represent explicitly. So when we can take our equation and solve it for y, that's representing it explicitly. But it would fail on situations like trying to find dy dx for that equation, x squared minus 2y cubed plus 5y equals 2. And the reason why it's going to fail on that equation is we can't come up with an explicit form. We can't solve for y. We can't put things into an explicit form. But surely that equation, that equation has a graph. And surely we could look at the graph and look at any point on the graph and draw a tangent line, which means, that tangent line would have a slope. So surely there would be a derivative for it. Well, in these situations, we need what's called implicit differentiation. It's just more chain rule, folks. The key for implicit differentiation is that we're going to assume that wherever we see a y, that y is representing a function of x. Y is a function of x. So let's see why I keep saying implicit differentiation is simply more chain rule. This is easy enough. If you're asked to d dx, differentiate with respect to x, the function quantity 3x squared minus 1 cubed, to get that derivative, you need the chain rule. And the derivative would be 3 times the quantity 3x squared minus 1, quantity squared, times 6x. Remember, that's 6x. That's the derivative of the inside function. And that, again, that's fairly straightforward because we can easily see what the inside function is. But folks, what if we don't see the inside function? What if we don't know what that inside function is? But what if it is just simply some function of x? 3x squared minus 1, that is a function of x. But what if we don't see that it is 3x squared minus 1? It doesn't change the process. So let's pretend that we don't know that inside function is 3x squared minus 1. Let's just pretend it's some function of x. And I'm just going to replace it with f of x. Well, notice we can differentiate it with respect to x. All I've done is replace the 3x squared minus 1 with a generic f of x, but we can still compute the derivative using the chain rule. We get 3 to come out front, so we'd have 3 times that f of x, quantity squared, and then the chain rule says times the derivative of the inside function. Well, the inside function f of x, the only way I could represent its derivative is with f prime of x. Okay, notice that that's the exact same process. It's the exact same thing. That's what we have at the top of the slide, that when we know the inside function, when we can see what the inside function is. So nothing has changed. It's still just using the chain rule. So let's go one more step. Now what if instead of seeing f of x, we just simply see y? Remember, y is the same thing as f of x. So what if y were in place of f of x? No, the process doesn't change. We can still d dx y cubed. And we're thinking that y is a function of x. So when we compute the derivative, it'd be 3 times the function of x squared, 3 times y squared, times the derivative of that function of x. Times, well, the derivative of that function of x would be y prime, or we write it as dy dx. And this is why you've noticed, ever since we started learning about derivatives, I've told you that if you had y equals something, it didn't matter if you called the derivative y prime or dy dx. And I kept stressing that, numerous times. This is why. I was laying the foundation way back when for this section on implicit differentiation. So before I leave this slide, I want you to see that, when you d dx at the top, when you d dx the function 3x squared minus 1 cubed, you use the chain rule. But if you don't know what that function is, you don't know that it's a 3x squared minus 1, if it's just represented by an f of x, you still use the chain rule. Or if it's just represented by y, you still use the chain rule. The key in implicit differentiation, the key is to assume that y is a function of x. And then we're going to ddx both sides of the equation. We're going to differentiate with respect to x, both sides of the equation. So in our first example that I will do on the board, I'm going to put in a couple of extra steps. And so these extra steps, it's just going to be, I'm going to replace y. Whenever I see a variable y, I'm just going to replace it with f of x. And then in later examples, I am not going to do this extra step. I will continue to mention it. I will continue to verbalize it, but I am not going to do it. So here's the first example. Let's determine dy dx for y squared plus 3y cubed minus 2y plus x cubed equals 5. So write this down because I'm heading off to the chalkboard to do it. And here we are looking at implicit differentiation, and so far we've seen it is nothing more than the chain rule. We've also seen why for a while now I've been interchanging using y prime and dy dx. But I said on the slides that for this first example, and this first example only, I'm going to put in an extra step. It's the step that I wish I had seen when I was learning calculus. When I was learning calculus, I'll be as honest can be, I didn't know where the dy dx was coming from. I would just occasionally toss it in and hope for the best. If I had seen this, if I had seen one example done how we're going to do this one, it would have stuck with me. Hey, it's nothing more than the chain rule. So let me put in the extra step, and I'll put it in this extra, or this reddish colored chalk. The extra step is we're assuming y is a function of x. So I'm just going to replace every y that I see with f of x. So I would have f of x, and for this y, f of x for this y, f of x for that y. Oh, that's an x, so I leave it alone. So that's an extra step that I'm putting in. And I'm just putting it in for this example only. I'm not going to do this in the future. I will continue to verbalize it, but I won't actually write it down. Next, once I've done that, since everything is in terms of a function of x, I ddx both sides of the equation. I differentiate with respect to x the left side of the equation, and I differentiate with respect to x the right side of the equation. Alright, so here we go. Over here we go term by term. The derivative of some function of x squared. Well, the chain rule tells us that would be 2 times f of x to the first power times the derivative of this function. That's the chain rule. Well, the derivative is f prime of x. Plus, move to this term, get the derivative. So the 3 comes out front, so I have 9 times f of x squared times, the chain rule says, got to get the derivative of that function. Well, that derivative is f prime of x minus 2. Okay, the derivative of f of x is f prime of x plus, well, that's friendly, the derivative of x cubed is 3x squared, and the derivative of 5 is 0. Now I go back and I resubstitute. Everywhere I see an f of x, I'm going to replace it with y. That's kind of undoing what I did here with the red colored chalk. And everywhere I see f prime of x, I'm going to replace it with dy dx. So I'd have a 2y dy dx plus a 9y squared dy dx minus 2 dy dx plus 3x squared equals 0. To determine dy dx, we have to end up with dy dx equals. So we have to take this equation and solve it for dy dx. So here's what I would do. I'm going to do two steps at once. First, I'm going to subtract 3x squared from both sides of the equation. Then that will leave me with these three terms that have a dy dx in it. So with these three terms that have a dy dx, I can factor out the dy dx. So I'm going to do those two steps at once. And I have a 2y plus a 9y squared minus 2 dy dx equals a negative 3x squared. So then my final step is to divide both sides of the equation by 2y plus 9y squared minus 2 to get dy dx equals negative 3x squared over 2y plus a 9y squared minus 2. All right, so going forward, I'm not going to do this step, and then there would be no need for me to have to do this substitution step. So what you'll hear me doing going forward, instead of writing this step down, we're going to ddx both sides of the equation, and you'll hear me say, remember this is a function of x. Y is a function of x. So when you get its derivative, you have to use the chain rule. So its derivative would be 2y, and then the chain rule, times the derivative of that function of x. That's the dy dx. So let's head back to the slides and see what is next. All right, hopefully you are starting to see that this is nothing more than the chain rule. Let's look at another example. You know, going to have three parts. Write down all three parts because I'm sure I'm going to ask you to do one of the parts. So part A, we're going to find dy dx for x squared minus 3x squared y squared plus 2xy squared equals 3. In part B, we'll find dy dx for 2 sine x cosine y equals 1. And then in part C, we'll find dy dx for the sine of xy equals x squared plus y. So get this written down because I'm going to head off to the chalkboard to work through them. All right, this example had three parts. I only have two of them up on the board right now. We're supposed to determine dy dx for part A, x squared minus 3x squared y squared plus 2xy squared equals 3. So I start off. I'm going to ddx both sides of the equation. And here we go, left side. So when we ddx x squared, well, we know the derivative of x squared is 2x minus, well, look at this. We have two functions multiplied together. I'm going to need the product rule. Because it's preceded by a subtraction sign, I better put the product rule inside parentheses or I'll make a careless mistake. So, product rule. Product rule says derivative of the first function. Well, that's 6x times the second function plus the first function. And now when we get the derivative of this second function, when we get the derivative of y squared, remember y is a function of x. So we'll have to use the chain rule. Y is a function of x. Y is a function of x, so its derivative is 2 times that function of x times the derivative of that function of x. dy dx. Moving on. Plus, oh boy, notice here, again, we have a product rule. So we crank this through the product rule. Since it's preceded by an addition sign, I'm not going to put the result of the product rule inside parentheses because I don't have to worry about a careless sign mistake. So here we go, cranking this term through the product rule. Derivative of the first function is 2 times the second function plus the first function times. Okay, now the derivative with respect to x of y squared. Remember, y is a function of x. So its derivative is 2 times the function of x times the derivative of that function of x. The chain rule comes into play. And then this is 0. All right, we got to do some cleaning up here. So we have a 2x. I'm going to distribute the negative, and I'm going to multiply these two things together at the same time. So it's a minus 6xy squared minus 6x squared y dy dx plus a 2y squared plus a 4x y dy dx. Keep in mind we're trying to determine dy dx. So I want to get all the terms that contain dy dx on one side of the equal sign. And I have two terms that contain a dy dx. So you know what, I'm gonna add this to both sides of the equation, and I'm going to subtract this from both sides of the equation. I'm taking these two terms to the right side. So that leaves me with a 2x minus 6xy squared plus a 2y squared equals a 6x squared y dy dx minus a 4xy dy dx. And then on the right side I can factor out the dy dx and then a little bit of division gives me 2x minus 6xy squared plus a 2y squared all over 6x squared y minus a 4xy. That is dy dx. Okay. Part B. Let's start out with d dx both sides of the equation. Notice we have a product rule on the left side here. We have a function 2 sine x times another function cosine y. So we start off, we use the product rule. So here we go. The derivative of the first function, well, that's a 2 cosine x times the second function, cosine y, plus the first function, 2 sine x, times the derivative of the second function, cosine y. Now remember, y is a function of x. It's an f of x. So when we differentiate that, we know the derivative of cosine is negative sine. So we have negative sine, that function of x, it's just y. Then you have to do the chain rule, the derivative of that function of x. It's dy dx. And then over here on the right, well, that derivative is 0. So, just kind of cleaning this up a little bit. We have 2 cosine x cosine y minus 2 sine x sine y dy dx equals 0. Now I personally would add that to both sides of the equation to get 2 cosine x cosine y equals 2 sine x sine y dy dx. And then just simply divide both sides of the equation by 2 sine x sine y, and we get 2 cosine x cosine y over 2 sine x sine y equals dy dx. In fact, I could go a little bit more. I could simplify a little bit. I mean, hey, the 2's would cancel out. Cosine x over sine x. That's cotangent x. Cosine y over sine y is cotangent y. And I'm not going to go any further. So that's part B. So let's look at part C. Get this erased. So part C is the sine of xy equals x squared plus y. Yes, the first thing we should do is d dx both sides of the equation. All right, so here we go, d dxing the left side. The left side is sine of xy. Okay, we know when we differentiate, we know the derivative of sine is cosine. So we have the cosine of xy. Now we have to do the chain rule. We have to differentiate the xy. So when we differentiate the xy, I mean we have a product rule there. So I better put down a bracket here. So when we're differentiating the xy, we have a product rule. So here we go. Derivative of the first function is 1. So we have a 1 times the second function plus the first function, x. Now the derivative of the second function, y. Y is a function of x. Its derivative is nothing more than dy dx. All right, over here on the right side, derivative of x squared is 2x. Oh, the derivative of y. It's just the dy dx. Okay, now we have to solve for dy dx. We have to get dy dx by itself. So what I would do right now, I would distribute this cosine of xy. To have y cosine xy plus x cosine xy dy dx equals 2x plus dy dx. And let's see. You know what? I'm going to subtract this over here and subtract this over here. Whoops. And then once I get my dy dx's on one side, you know I'm going to factor it out. So I'm factoring out a dy dx. That'd leave me with a 1 minus x cosine xy. So that's factoring out the dy dx. Then divide both sides of the equation by this to get a y cosine xy minus 2x over 1 minus x cosine xy. That is dy dx. I'd like you to practice a couple of these real quick. So in the book, see this is section 3.8. In the section 3.8 exercises, right now, I would like you to try numbers 30 and 32. So pause the video, do numbers 30 and 32. After you've done them, you know the drill. Restart the video. I'll be here at the board working through them. All right, folks, number 30, you're supposed to get dy dx for x. X plus 2y equals the square root of y. I went ahead and did the first step of rewriting square root y as y to the 1/2. So we d dx both sides. And see, derivative with respect to x of x is 1. Derivative with respect to x of 2y, that's just a 2 dy dx. Derivative with respect to x of y to the 1/2. Well, remember, y is a function of x, so it's 1/2 y to the negative 1/2 times the derivative of that function of x, which is dy dx. And, you know, I don't like that negative exponent. So I'm going to get rid of the negative exponent, going to move it to the denominator, and instead of writing it as y to the 1/2 down here, let me just make it the square root of y. Okay, so what to do? Why don't I subtract this term over here? So I just have a 1 equals a 1 over 2 square root y dy dx minus 2 dy dx. Then I factor out the dy dx, and then I divide both sides by this mess, and I get something that just looks horrible. There's no way the back of the book would have an answer like this, because it's a fraction. Down here you have a fraction. So here's what I would do, just to get rid of this complex looking fraction. I would multiply the numerator and the denominator by the number 1 square root, or 2 square root y over 2 square root y. Then that gives me, well, 2 square root y times 1, that's 2 square root y. In the denominator, 2 square root y gets multiplied by this. I get a 1. And when 2 square root y gets multiplied by 2, it leaves me with a 4 square root y. And I am not going any further. Hopefully you got something like that. Hopefully you at least got to this part right here. Number 32. Yeah, you start off by ddxing both sides of the equation. Okay, see the derivative of tangent. We know the derivative of tangent is secant squared. So we have secant squared of x plus y times, okay, now we have to get the derivative of x plus y. Well, the derivative of x plus y, I better put that in parentheses. Derivative of x is 1. Derivative of y, well, that's just dy dx. And then over here, we just get a 2 dy dx. All right, what I would do is I would distribute the secant squared x plus y to get a secant squared x plus y plus a secant squared x plus y dy dx is equal to a 2 dy dx. And then, you know what, I'm going to subtract that from both sides of the equation. That way I get all of my terms involving a dy dx over on the right side. And, you know, once you get them on one side, then you factor out the dy dx. And now I can divide both sides by this mess to get secant squared of x plus y over 2 minus secant squared of x plus y equals dy dx. Hopefully you got that. So that was 30 and 32. Let's head back to the slides and see what's next. All right, hopefully you're feeling a little more comfortable here with implicit differentiation because you know you really understand the chain rule. Let's look at another example, final example in this section. We are going to determine an equation of the line tangent to the curve given by x cubed plus y cubed equals 2xy. And the point of tangency is 1, 1. So make sure you write this down because I'm heading off to the chalkboard to do it. All right, this final example, it's an old familiar topic, coming up with an equation of a tangent line, tangent to a curve at a given point. So we know the point of tangency is 1, 1. All we have to do is come up with the slope. And we know slope of a tangent line is given by the derivative. So we have to determine dy dx for this equation. So no biggie, we start off by ddxing both sides. And over here on the left side gives us a 3x squared plus, again remember that's a function of x. So the derivative is 3, that function of x squared, times the derivative of that function of x, which is dy dx. Here on the right side, oh boy, we have the product rule. So the derivative of the first function is 2 times the second function, plus the first function times, okay, the derivative of the second function, just the dy dx, that's not bad. So, you know what, I'm going to subtract 2y from both sides of the equation. And I'm going to subtract the 3y squared dy dx from both sides, just so I can, you know, that way I get all my dy dx's on one side, so that gives me, what, a 2x dy dx minus a 3y squared dy dx. And then factor out the dy dx. Then do a little division. So we have dy dx. Is this mess. So to get the slope of the tangent line at 1, 1, we put 1 in for the x's, and then we put 1 in for the y's. So at 1, 1, let me pull it up here. At 1, 1, the slope of the tangent line is, alright, so 1 goes in for the x's, so I'd have and 1 goes in for the y's. So I have a 3 minus 2 over a 2 minus 3. That's 1 over negative 1. Look at that. The slope of the tangent line is negative 1. So we know the point of tangency. We know the slope. We use point slope form. So we have a y minus 1 equals negative 1 times x minus 1. And I know most of you say, hey, distribute that to get a negative x plus 1. And then go ahead and add 1 to both sides to get negative x plus 2. I know most of you like to see your lines in slope-intercept form. But that was just revisiting an old topic. So folks, hopefully you're seeing we did really nothing more than the chain rule. It was a little more disguised now. This exercise set is really important for the next section when we look at related rates, because it's nothing more than implicit differentiation, which is nothing more than the chain rule. So it's imperative you do these problems to get practice on implicit differentiation. So at this time, you're good to go. You can do the exercises in section 3.8, so go do them. And thanks for watching.